Then, lesson 15, series versus parallel circuits. And I'm going to try and get this done before lunch. So we will learn the difference between a series and a parallel circuit. Now, this is something you should have learned at the end of year 9, but I'm going to be honest with you, I've taught year 9 for a couple of years, and most times, the last couple of weeks with parallel and series circuits is just it doesn't work very well. By that point in time, students are like looking forward to the holidays. They're not listening. They're not taking everything in. So this is going to be a good chance for, at the start of the year, you guys to spend some time and really zero in on the difference between these two types of circuit design. Leading up to this, we've been discussing the differences between, we talked about, last lesson we talked about parts of a circuit. We sort of talked about, well, what makes up a circuit? We've got batteries, light bulbs, switches, and wires. And then we sort of spent some time talking about, well, in a battery, who can tell me, left or right, which one's negative?
Right.
Left is positive. Left is
Left
positive.
Right is negative.
And right is negative, because in this case, it's a big long stick that can be snapped in half, and then that snapped stick can make a positive sign, because you can't snap that big thick stick. That's just how I think about it. Again, you might want to come up with a different way of thinking about it, but yeah. Before this, by the way, we finished up talking about our ideas of current being the amount of electrons moving through a wire, or the amount of charge moving down a wire, voltage being that push that's pushing the water through the down through the river, that's pushing the electrons through the wire, and resistance, the stuff that is slowing it down. So when we talk about wires, we usually just say, even though, yeah, sure, the electrons need to push through the wires, we're going to assume that they barely have any resistance. And we're going to assume that all the components follow Ohm's law, V equals IR. The last thing we talked about was voltage drops. A voltage drop is considered to be when something loses energy. Remember, voltage is linked to the amount of energy. So it needs to, if I've got a 6-volt battery, that 6 volts is going to go all the way through the battery, but when it goes through the light bulb, it has to push its way through the light bulb. So when it comes out, it's going to have low energy. In fact, it's going to have 0 volts worth of energy, no energy left, because it lost all of its energy pushing its way through that light bulb. Today, what we're going to talk about is the difference between a series and a parallel circuit. So let's get started by putting up 2 different circuits. On the left, we have something called a series circuit. In a series circuit, the current only has one path to flow through. It can go up through this resistor, through this resistor, through this resistor, and back. It only has one path. And it's called, like, if you think about it, a TV series only has one order you can watch it. First, second, third, fourth, fifth. A book series only has one order you can read them. The first book, the second book, the third book, the fourth book, the fifth book. You can't do multiple, you can't read it in whatever order you want. And so that's why it's called the word series, because it's an order. It's a path that you have to follow through. So current only has one path. In a parallel circuit, though, there are multiple paths for the current to flow through. This is like the difference between having a river that then branches off. And that river might come back together at the end, but ultimately it can go in any number of ways. There are multiple paths in parallel. There are multiple paths the circuits go through. So if you imagine the current, so the current comes out and it gets here, and it has to make a choice. Do I want to go down, or do I want to go to the right? Some electrons will go down. Some electrons will go to the right, and they might choose to go to the right again. Some electrons will go down. Some electrons will go around. But they will all combine to get back to the battery. Why is it called parallel? Because all of these lines are parallel. You can go down any of those lines you want, okay? And you might refer to parallel, something in parallel would be, I guess, your subjects. So for example, you are taking maths and English in parallel. What that would mean is you are taking maths and English and science at the same time. You don't have to finish English. You don't have to finish your English course this year before you can do your maths course. There are some serious components to it because you can't do year 10 maths until you do year 9 maths. But yeah, essentially, your subjects are usually done in parallel. You do them all at the same time. Yeah, so good point. Thanks, Reese, for answering that question to me. The electrons would move from negative to positive, but because we're talking about conventional current, we always start at the positive. Now, just because I know some of you guys here are going to be a little bit, well, actually, probably none of you guys will think this, but just so you know, you can have combinations of the two. You can have a parallel circuit. I'll just do this over here. You can have a parallel circuit that has a series component to it. So you could have a so this is a parallel circuit with a series component because here is the parallel part and here is the series part. One, then two, one, then the other. But we're not going to deal with that stuff because this stuff down the bottom is a little bit more too complex. We're just going to ignore this. But some of you guys are probably smart enough that you could understand it, but I'm just going to ignore it. Let's draw some pictures here. Here we go. This is it in pictorial form. We can see there is only one part, one wire that connects everything. Whereas here you have one wire, two wires, 3, 4, 5, 6. You have lots more wires in a parallel circuit. Okay, so that's the basics. Now we're going to crank it up a notch because we're going to start to now understand why a parallel circuit is sometimes better than a series circuit and why a series circuit is sometimes better than a parallel circuit. So this is going to get interesting. On the left, we have a parallel circuit. On the right, we have a series circuit. Can someone tell me really quickly how I can tell the one on the left is a parallel circuit? How did I know that?
Separate branches.
There are separate branches. Good word. So I actually did not use that word. Separate branches is a good point. That's exactly what's going on here. We've got branches that's branching off. Now, can someone tell me an observation between the difference between a parallel circuit and a series circuit?
The difference?
Yeah, what's the difference?
I got this. So like one goes like constantly and never stops. There's only one way, and the other one has multiple ways.
Yep, good. That's correct.
So,
now, while you're there, though, I want you to tell me, looking at this picture, what is visibly different about the two circuits aside from the paths?
one's lit up. That like the left side has 3 lit up, and the right side doesn't.
The left side has them. Yeah.
The right side has shared like electricity, so it's like weaker.
So the left side is bright, the right side is dim. And I don't know who said that. So I'm just basing it off the sound of your voice, so I can't actually see you talking. I think that was either
I'll take credit. Yeah.
it was either Brendan, Jason, or Vincent. I can't actually tell, but one of you guys said sharing electrons. And yeah, that's correct. It's sharing energy. And that's sort of exactly it. It is sharing energy. Why does the series circuit share energy but the parallel circuit doesn't? That's something we're going to talk about now. And I'm going to do that by talking about each of these circuits independently. So first, we're going to look at this idea here, splitting the current flow. So, give me a sec. So, so some of you guys are saying we learned this last year. You would have learned this briefly last year, so this shouldn't be too new to you guys. Let's take a circuit here. Let's take 6 volts. We're going to put 6 volts through these 2 globes here. I'm going to say this globe A and this globe B are the same type of globe. Okay, they have the same resistance. Now we know that in order for this to work, as any circuit should, at the end it should have 0 volts, no energy left. Now, if it's got 0 volts, it's going to have to give some of its energy to get through this first bulb. It's not easy. It has to give away some of its energy to get through this first bulb. How much energy does it use up to get through that first bulb? Well, it's going to use up 3 volts. And that means we're going to go from 6 volts down to 3 volts. And how much is it going to use to go through this second globe? It's going to use up 3 volts. So it's going to go from 3 volts down to 0 volts. Okay. Let's talk about, I'm going to change colors for a second. I'm going to go to green. Let's talk about the current. If I had, let's just say this is 2 amps, right? When I go through that first bulb, I've still got 2 amps because the flow isn't going to change. There's going to be no change in flow because there's nowhere else for the electrons to go. And after it goes through the second bulb, there's still going to be 2 amps. All right. So let's talk about this again really quickly. Can you guys see what's going on here? The voltage gets dropped. That's called a voltage drop. 3 volts gets dropped here, 3 volts gets dropped here. Meaning at the end we have 0 volts. But the current is the same all the way through the series circuit. So I'm going to write down on this slide what this means. What this means for us. No one's playing tic-tac-toe, John. What this means is we should have the voltage drop must be 0 at the end. The current at the end and the start must be the same. So if we look at this example here, we've got 6 volts at the start, 2 amps at the end. We've got 0 volts at the end and 2 amps at the end. So yeah, the current's the same and the voltage, all the voltage is gone. So this is for a, is this on the left? Is this a series or a parallel circuit? Someone's already said in chat. Give me a sec. Okay. Is the circuit on the left a parallel or a series circuit?
Series.
Series. Good. Thank you. This guy here is a series circuit because it's one after the other after the other. This one here is a parallel circuit. Let's look at what happens for the parallel circuit. Let's say I put 2 amps in. Now, after I put these 2 amps in, it's going to be interesting, right? Because those 2 amps are going to reach a junction. Now, at that junction, the current doesn't care if it goes up or down because it's the same resistance at the top or the bottom. So that means the current's going to split. we're going to have 1 amp at the bottom and 1 amp at the top. Can you guys see how the current has split? That means here, what's the current going to be at this part of the wire? What's the current going to be at the very top right?
Still 1.
Still 1, yeah. It's going to be still 1 here.
But the volts would be the same.
Yeah, let's watch this in a second. So the current's going to be 1 amp. And then when it gets back together, we're going to have 1 plus 1, which is 2 amps at the end. So it's just like in the series circuit, 2 amps at the start, 2 amps at the end, 2 amps at the start, 2 amps at the end. But now let's look at the voltage drops. The voltage drops, we've got 6 volts here. Now, if the current splits, right, this is the part that students get a little bit lost at. If the current splits, that current, think about the river, still has the same amount of energy. So this current still has 6 volts, and this current still has 6 volts. So the current is split, the electrons have split, but the electrons still have that 6 volts worth of energy. They still want to get to the end, still want to get to that positive charge. So they've still got that 6 volts. But now it now needs to get to 0 volts at the end, which means that each branch needs to get to 0 volts. So how much voltage is it going to lose as it goes through that top light bulb? Someone said it. Chat. It is 6. Yeah,
6.
You're right. It's going to lose 6 volts. And this one at the bottom is also going to lose 6 volts. So we can see now why a parallel circuit is going to be brighter than a series circuit. In a series circuit, the voltage is shared. But in a parallel circuit, the voltage is not shared. What is shared is the current. The current is shared. So the voltage isn't shared. So each of those light bulbs gets 6 volts. And it has to lose those 6 volts before it gets back to the battery. So that's why. It does have less current, which does mean that there's going to be a bit of a trade-off, which means it's going to be a little bit less power. But overall, it's not going to make that much of a difference. And in the small scheme of things, it's just going to mean those light bulbs are brighter. Now, I'm going to go through one more idea. No, I'm going to go through 2 more ideas, and then it's going to be it. The first idea is, does the order matter? The amount of time that I've tried to explain, and I've tried to explain this so many times to students, and each time, you know, I do a little bit better, but I still haven't got there yet. Let's just say I put 10 volts into this circuit, right? Now this resistor is 2 ohms. That's like imagining trying to climb over a small hill. This resistor is 8 ohms. That's like trying to climb over a wall. And what happens is that 10 volts gets through the first light bulb really easily. So it only will lose, like maybe say it only loses 2 volts. Okay? Whereas when it goes through the big resistor, the big light bulb, it's going to lose 8 volts worth of electricity, bringing us down to 0 volts at the end. Now, if I look at the one on the right, let's just say I took this one. I've got 10 volts at the start. I'm going to lose 8 volts over the first light bulb. And then I'm going to lose 2 volts over the second light bulb, which is going to give me 0 volts at the end. Now, the reason why people get confused by this idea is that they start to think of light bulbs and these sort of things. They kind of think of them as a runner. They go, oh man, if I was an electron and I was running through this circuit, I would be really tired if I had to do the 8-volt one, and then I probably would, then I wouldn't have as much energy to go through the 2-volt one. So it would probably would be a bit different. And then the same thing occurs for the one on the left. They might be like, oh, the first one will be easy, but the second one will be hard. And the one that annoys me is when I do this. I say, okay, here's 2 light globes, right? This one is 1 ohm. This one is 1 ohm. And I go to them, right? This one is hooked up to the positive side of the battery. So the current goes this way. And I ask students, and trust me, I have asked students this for 4 years and they always get it wrong. I say to them, which light globe is brighter? And I guarantee someone in this class is going to get this wrong. I say to them, which light globe is brighter? And they say, well, obviously the first bulb is brighter because the current reaches it first. They think about it like a runner. If you're running up to a hurdle, you will do a lot better job at climbing over the first hurdle than the second hurdle. But if they're the same resistance, if the resistance is the same, you will lose the same amount of voltage over this resistor as this resistor. The order doesn't matter. What matters is the resistance. And if they're the same resistance, then they will lose the same amount of charge. They will lose the same amount of voltage. Yeah, they are equal. So you guys sort of figured it out. But like, trust me, when you guys see that question on the test, I want you to remember that. I want to show you guys another way to think about this. Let's think about this instead using some kind of physical system. In the one on the left, I'm going to pour a bunch of water. This is a curtain, by the way. It doesn't look like a curtain, but imagine that it's a curtain, yeah? I'm going to pour a bunch of water in this one on the right. What's going to happen is that water is going to come out, and eventually it's going to come out the other side. And this one comes out the other side as well. And so you say, okay, what's your point? So I don't know what's happening behind that curtain. Okay, I don't know what's happening behind the curtain. But what I do know is that water is coming out of both of them. And it's the same amount of water. It doesn't matter. It's the same amount of water. So it doesn't matter whether I pour water down the one on the left or I pour water down the one on the right. Also warning, this could be a bad analogy. Okay, so let's have a look what's behind the curtains. In the one on the left, I have a really big pinwheel, and this guy turns around, and what's happening is I'm filling it with water and it's pushing this wheel around. Then the water still has a bunch of energy left. It hasn't got as much energy, but it's still got a bunch of energy, and it will push the small one, and eventually that water will come out the other side of the In the one on the left, I've got the little wheel comes first, and that will spin that little wheel, and then the water will come down and push the big wheel, and then eventually it will come out the other end. The lesson here is, again, the order doesn't matter. It doesn't matter whether you push the big wheel first or the big wheel second, because you know that the water is going to come out the other side. You know that if the water is going to come out the other side, then it must have pushed the wheel. The energy is going to get used up by the system, no matter what order it goes in. Same way that it doesn't matter whether the, so going back here, it doesn't matter whether the voltage gets used up by the 2 ohm or the 8 ohm resistor first. It's going to lose all its energy as it goes through the system. So it doesn't matter which one loses the energy first. It doesn't matter whether the big wheel or the small wheel uses the energy first, because all of the energy is going to be lost by the end. It's going to always end up at 0 volts at the end. Doesn't matter the order. So again, if you had 2 pinwheels that were exactly the same, it doesn't matter whether the first one gets turned first or the second one gets turned first. They're both going to lose the same energy because they both are going to turn. They both are going to, it doesn't matter the order. I don't know how many times I've tried to explain it to students and they just don't really get it. So we're going to talk about this stuff next time. What I'd like you to do is your last task is this. I want you to answer this question. And you know what? I'm not even going to, I might even, yeah. I want you to write this question answer down. You guys can answer this question. I want you to answer this question maybe here or in chat, or you can write it. I do want you to at least write it down in your book. The idea is I want you to write this down because this is a question on the test. I'm not even going to lie. I'm not even going to pretend to you guys, oh, maybe this is a question. This is a question on a test. It's usually out of 3 marks. To me, the 3 marks are, I always mark it for 3 things, and I always look for 3 things. The first thing is you need to say what's the difference between a series circuit and a parallel. Because a lot of people say, oh, the series circuit will do this, but they don't say, oh, a parallel circuit has branches. The second thing I look for is which is brighter. There's another mark. And then I want to know why. And we've just talked about why. Let's go have a look at some of the answers that you guys thrown up already in chat. And then that's going to be the end of the lesson here, ladies and gents. Oh, there's a fair bit in chat already. Let's grab a look here. Yes, I saw what you said, Angus. Okay, so parallel. Yep, parallel is brighter. Great. That's not a sentence yet. Which one is the one that goes straight? Okay. Series is one that goes straight. Yep, pretty good. Thanks, Jess, for fielding that one. Here we go. Reese has got a parallel because each bulb will consume 9 volts. On a series circuit, the volts will divide. Beautiful, Reese. That's 2 marks, not 3. The reason that I'm giving you 2 marks for that answer is because you haven't said what the difference between a series and a parallel circuit is. Because the series circuit, the bulbs will only have 4.5 volts, whereas a parallel circuit, they will have 9 volts. Okay, good. Jason, again, 2 marks. I want you to kind of address the difference. So like Reese, what I mean is this. Say something like this. In a parallel circuit, there are multiple paths. So and then you might then go, so the voltage, so the current splits, but the voltage is the same. And then you can then take something like that and use that to write an answer. So I want a different, and I think in the test I actually write a little bit different, like a little bit differently, but it is pretty much, you need to say why are they different? I don't want you to just say, oh, you know, you need to say what is a series circuit. But yeah, if you say the voltage splits, if you say the voltage splits in a series circuit, you could just add this to the end of your answer, Reese. The voltage splits in a series circuit because there is only one path for the current to flow through. Perfect. That would be the answer that I would give to something like that. Ladies and gents, I think that's about it.